Okay. Good evening, everyone. My name is Teja, and I'll be the instructor for this course. So the course is IDS 576. So I hope everybody is for 576 and not some other course. Okay. So today we'll go over a few things, which is going to be, I'll introduce the course. What is the expectation from this course. I'll go through some course logistics. I've already posted the syllabus on the Blackboard, so you might have seen it. And today we're going to discuss, really going to jumpstart and discuss a few things. Something, if you have already done IDS 572, we'll go through classification, so a few stages in classification that you've already seen. And then we'll look at one key technique, which is called back propagation. And then we'll just touch upon feed-forward neural networks. Okay. So applications, I have not really written a huge introduction slide here because I think most of you already know a lot of applications of machine learning and of course of deep learning. Especially in the past few years, there has been a lot of work in this area, and I think every 6 months you see a lot of papers doing a lot of exotic things in deep learning. So we'll kind of get to them as we progress in the course. But in terms of broad categories, the way I look at it, deep learning applications have been quite remarkable in vision, by which I mean computer vision, speech, which is speech processing like Siri and Alexa and so on, text is natural language processing, language like machine translation, and then control. When I say control, it's basically reinforcement learning or robotics. Think of it that way. Okay, so the course is divided into roughly 2 parts, and hopefully if there is scope or time, we'll cover the third part. So the first part is going to be some deep learning techniques. So we'll get into that towards the second part of this lecture, and we'll also look at something called probabilistic graphical models, which is a nice formalism which kind of unifies a lot of the techniques, some of the techniques that you've seen in the previous data mining course. Okay. And the third part is going to be online learning and reinforcement learning. I don't know how. So have you guys have already been exposed to any of these 3 topics or all of these 3 topics? None of the 3 topics. Okay, that's fine. So we'll go through each one of them. So online and reinforcement learning is kind of useful in online ads, and also reinforcement learning is potentially useful in making AI agents like self-driving cars and so on. So we'll get to them. So I have a couple of slides for each of these broad chunks of topics that we're going to cover in this course. So deep learning, one of the specific kind of remarkable features, remarkable feats was achieved at what is called the ImageNet Large-Scale Visual Recognition Challenge. Okay, so this is a challenge which has various different computer vision tasks like object detection, object classification, and a variety of other things which have been added on as the challenges progress. So the challenge started, I think, in 2010 or 2009. So the data set itself has about 22,000 categories, which is 22,000 labels, and the number of data points or the examples is about 14 million images. They don't use the whole data set for all the tasks, but so the scale of the data is really humongous. Before this, I think the previous closest large data in vision was the Pascal visual object detection or classification challenge, which had an order of magnitude lesser labels and an order of magnitude or 2 orders of magnitude lesser images. So for this data set and this challenge, which was run for about, and which is still being run, or probably it got stopped this year, you can see. So this task is about, the specific task that I'm going to focus on is image classification. For this task, they said, okay, we're going to give 1,000 labels, 1,000 categories. That's what I mean. Okay, actually use my point. Okay, and about 1.5 million images, and you have to predict 5 categories for a test image, and one of them hopefully is correct. Okay, you can be wrong in 4 of them, but you can at least, if you're fine with, you can at least tell out of 5 guesses you can make one good guess, it's good enough. And so this classification error is a slightly modified definition. It's not the classification error that you see in your introductory course, but that's fine. So you can see the change in classification errors of the best performing submissions for this challenge as a function of the year it was run. And from 2011 to 2012, there was a huge change, about 10% difference in the classification error. So, and this is the held out test error which only the organizers have. Okay. So this 10% difference was, very remarkable for the community and of course the machine learning community at large, and it was achieved through what are known as convolutional neural networks. So we'll get to them in probably lecture 2 and 3. Okay. So neural networks are not new, as you guys probably already have seen. I think in IDS 572 there was a brief introduction to multilayer perceptrons. So neural networks are not new. They've been around. The concept started around 1960s. And it was applied for handwritten digit recognition back in 1998 by a researcher by the name Yann LeCun. It was not mainstream till about 2010 and 2012. 2010 was when it was successfully, or deep networks, some architecture was successfully used for speech recognition task, and 2012 is the year when you saw the performance improvement in the previous slide. Okay. And what changed from these years to the previous years is access to really good compute power and access to really good data set. Okay, but one of the big caveats is that people flash ImageNet performance improvement as a big win for deep learning, but deep learning achieves good performance only on some tasks. So there are some other tasks in the same challenge, ImageNet large scale visual recognition challenge, where deep learning has not given us the same absolute performance improvement, and so it's not played hyped up in the media, and so it has typically not worked really well beyond classification, but you will see some other newer architectures which are doing really well. So we'll see them in the later part of this course. And so so we can think of it in terms of the Gartner hype cycle. I don't know how many of you know that hype cycle. So either we are on the we're definitely on the earlier part of that hype cycle, where either we are looking at deep learning technologies exploding, or we are still on the exponential side of that curve, or we are at the top of it, or whatever global optima. So I think there is a lot of scope for improvement in terms of engineering, system building, and applicability in a lot of other data sets. So the data sets that deep learning has shown success is somewhat is a large amount of the internet data set, like vision, like images and text and so on. But still there's a lot of scope for using it in a lot of other areas. Okay, so the second huge chunk of this course, hopefully it will be huge depending on how many lectures we'll use for deep learning. So it's going to be about graphical models. So graphical models are, it's a fancy name. It just says, okay, I have a joint distribution or a bunch of random variables, and I'm going to represent it as a graph. Okay, the graph can be a directed graph or an undirected graph, and so each, based on these two categories, there is a lot of work which has been done. So what do you do with a graph, a graphical representation of a joint distribution? All you try to do is try to compute marginal distributions, for example, or conditional distributions, and so on. So those are the computations that you want to do once you can represent a joint distribution as a graph. So some of the special cases that you might have seen are mixture models. So Gaussian mixture models are a special case. Hidden Markov models, which you might have seen in speech recognition or speech processing, are also special case. Kalman filters, which you might have seen in electrical engineering curriculum undergrad or something like that, they are also special cases of graphical models, and they were in vogue before the deep learning hype. So it's kind of important that we kind of use this. It's a nice formalism which helps you model a lot of unstructured data, and it's been quite popular in the bio related data set kind of threads. Okay, and the last chunk, hopefully we can get there. Why is there a plus there? Okay. is going to be online or reinforcement learning. So here I've just snapshotted some of the application areas of these techniques or these frameworks. Control, as you know, people are trying to build autonomous drones for delivery. A lot of companies are also trying to do autonomous driving. Not the whole part, but some parts of such an architecture, such a system, huge system, will include some of these techniques like online learning and reinforcement learning. In operations, how do you retain customers? How do you incentivize customers? How do you manage your inventory? All these can be cast as something called Markov decision processes, and then you can kind of a step away. You'll kind of have to use online or reinforcement learning techniques. Okay, and the recent, I guess, claim to fame is not too recent, but 5 years ago, 2000. Okay, I don't remember. 2000. Okay, it's not 5. Oh yeah, maybe 5 years ago or 4 years ago. This is the use of deep reinforcement learning solution. So when I say deep, it just includes a deep network as a sub-block in the solution. It was used to build an agent, and that agent was able to play. Okay, one second. Okay, and the agent was able to play a game. Okay, so this is the game of. It's called Breakout. How many of you have heard about this game? Okay, so this is a game. So this is a part of the Atari environment. So it has a lot of games. I think I don't know, probably 50 games. So for this particular game, the objective was to design an agent, an artificial intelligence agent, which would control the paddle at the bottom and try to score. Okay, so the score is the feedback. I mean, it's same as what we do. We also, will control the paddle at the bottom and try to get as many bricks down as possible so that we maximize the score. So this paddle is being controlled by an agent called DQN. Okay, deep, I guess Q is for Q function, but whatever, Q network agent, DQN agent, and the agent learns on this game, as in it has the access to the simulator, so it kind of learns over a period of a lot of days. I think in this case it was about 14 days of non-stop learning, after which it has figured out how to play this game. And so you can see a very, very clever strategy. I would say this is not something you would figure out in the first 2 minutes, but ultimately it has figured out how to play this game really well. And so this is one of the this is one of the examples of modern reinforcement learning. The big part of reinforcement learning or online learning is going to be what is the simple intuitive concept of trial and error. So you try something, you'll see what the score is. Maybe you're not getting the score or you're getting the score. Based on that, you change your actions. So that's a trial and error framework. Okay, so those are the 3 blocks that we're going to look at in this course. In the meantime, I'm going to switch back to the syllabus to just go over the course logistics really quickly. I don't know what happened. Okay, can you guys see? Okay, so the logistics is we are meeting 6 to 8:30 on Wednesdays. We have a TA, Minghong Su. She is not here. So she is a PhD student in the MIS branch, and she's going to be the TA for this course. Most of the course material will be available on Blackboard. In fact, because this is such a transient topic, there are a lot of courses which are being recently offered in several other institutions, including all the top institutions, CMU, Stanford, and so on. So I think a lot of material is kind of dispersed. So it's better to focus on the material that we're going to put up on Blackboard. Prerequisites, it's assumed that you know a little bit about linear algebra, so you're comfortable with matrices. Calculus is just needed for, I think, backprop. Statistics and probability to kind of understand what you're doing, right? I mean, you have a lot of examples, it's all data driven, so you need to understand some of the core concepts in statistics and probability. And also, we're hoping that either you know a little bit of Python or you will pick up Python in parallel to this course. Will not need any advanced level Python programming. It's just needed for importing your data, setting up your model, hopefully using some good modules already existing, and then training your models and visualizing the outputs. So how many of you have used Python for something or the other? Okay, I think 40-50% of the class. I have put up a couple of links to learning Python on the Blackboard on the lecture zeros page. So please look at that. If we have time today, we'll get to we'll see a small scripting session. Okay, so in terms of the remaining parts of the course, other than lectures, there will be 2 assignments and 1 project. Both assignments will this is the usual stuff, but one of the key points is you need to form groups of 3, so it's easier for you to also finish the assignments, and it's also easier for us to grade it. And once you form the groups, you cannot change it, and you'll communicate your groups when you hand in the first assignment. Okay, we'll release the first assignment in either the next class or a week after that, so either by lecture 1 or lecture 2. I'm going by the 0 numbering, so today is lecture 0. Okay, and so there'll be 1 in-class exam. I think almost this is probably lecture 10 or 11. It's going to be end of March after spring break, so you have time to study. The exam is closed book, no computers and no communication devices. In terms of grading, assignments are going to be total 30%, exam 25%, and the project 45%. So the details of what exactly constitutes a project in this course we'll put up on Blackboard. It is definitely not expected that you have access to infinite resources, as in really large data or really large compute power to do the projects. In fact, we'll try to be less ambitious while trying to set up projects. While you guys also choose projects, you need to be less ambitious. Tentative topics. There's a bunch of topics thrown in here, but we'll update you on the topics which will be covered on Blackboard. Okay. Any questions about the logistics? I think that was the fastest way of getting rid of logistics so that we can get to the course. Okay. So today we are gonna do hopefully slow ramping up into our course. Our course topics are going to be the last 2 points, which is backpropagation and feed-forward neural networks. But we'll do a slow, warm start by kind of recapping something that you've already hopefully done in IDS 572 or equivalent, which is going to be the classification task. So I hope most of you have done IDS 572 or have seen classification before. Who has not seen classification? Okay, so classification, so here I'm just taking a running example of vision. So here, let's say you've been given an image and you just need to output a label or a category, and it's quite simple. But so let's look at this block by block. So in vision, the input is typically going to be, let's say, an image or a video. Let's pick it's an image. If you just look at an image for a computer, it's going to be just a bunch of numbers, right? In fact, it's going to be just a 3-dimensional array. Let's say there are 3 channels in the image. Then it's just going to be a 3-dimensional array, and each pixel in that 3D array is going to be integer between 0 to 255, typically. Okay. So that's what it looks like to a computer initially. And for us, of course, we can process and see what's there in the image, and we can recognize objects in the image. But we want the computer or the machine to be able to kind of identify objects and so on, right? So another key thing about the data, especially an image, is going to be the image is going to look different, of course, based on some of these properties that I have mentioned here, like the location of the camera which shot the image. Let's say you took a picture of your laptop, the location from which you take the picture of the laptop the lightings, in fact this class has a lot of lights, so the light sources, the rigidity of the object. Let's say you're taking a picture of your bag. If the bag is full versus the bag is not full, it's gonna give a different pixel values, right? The three-dimensional array is gonna look different. And there could be other things like occluding objects, the background on which the object is placed, and as I said, if it's a bag, if it's half full, full or not full, across across the same manufacturer, there are going to be different bags. And so how does a machine, how will a machine be able to understand these variations? And in fact, the philosophical answer is the machine doesn't understand right now as of today, but we will try to see how the machine can still work well in terms of identifying objects in a dumb manner, in a relatively less intelligent manner. Okay, so we'll assume that we have, let's say, n training examples. I've represented them as x subscript I and y subscript I. So I is just an index for your training example. So you have this index number varying from 1 to n, right? You have n training examples. So xi is called the feature vector for the ith example, and yi is going to be label for the ith example. So let's assume that the labels are just let's say there are 10 labels, then the label yi is going to just take a value from 1 to 10, integer, let's say. Okay. In fact, let's assume that there is no ordinal relationship between the labels, so it doesn't matter. So 1 is not greater than 2 or anything like that. Okay, it's just a number. It's just a tag. Features, as you already know, are just functions of the data. So if you have an image, I can create features from that image, and that's what people used to do traditionally before deep learning. So we carefully hand design features. The specific features for vision or images were, for example, histogram of colors. So histogram of colors is very simple. So you have this three-dimensional array, which is let's say 128 cross 128 cross 3. So you'll pick you'll per 3 pixels you can kind of categorize it into certain types of colors, right? Let's say you spread out the colors. You give an index to each of the color. Then for each 3 numbers, you can see whether it's blue, whether it's turquoise, whether it's pink, whether it's red, or so on. And so you can create a histogram. And so that vector representation, you can call it a feature of your image. And similarly, you can create some more advanced features. For example, histogram of oriented gradients, scale invariant feature transform, and some other types of filters. So these are actually highly specialized features. So it's basically you've been given an image. These are just functions that operate on that image and output vectors, right? These were these are relatively new actually. Histogram of oriented gradients is probably from mid 2000s. So after a lot of effort from the computer vision community, such functions, such feature extractors were designed and were used to create this feature vector xi, and then you can use your shallow models like SVM or multi-class logistic regression, or classification, to classify your images. Okay, so this feature somehow kind of encode that there's a cat in the picture, there's a bag in the picture, there's a laptop in the picture, and so on. And also you can differentiate across them. With deep learning, there's almost no feature engineering, but there is still some insight from the data that you do take into account while designing your network architecture. So, for example, if it's a vision domain, which is what I'm describing here, you will kind of know that it's going to be an image, and so maybe a convolutional neural network is right architecture to use rather than a feed-forward neural network. Okay, so there is no hand engineering of very specialized features, but there is still your data kind of informs the network architecture that you're going to use and various parameters associated with it. Okay, so that's about data. I didn't spend too much time on it because we are going to be generalists. We are not looking in depth into one particular type of data set as of yet today. So let's look at models. Okay, models can be of many types. In particular, for classification, let's say I split the models into 2 kind of bins. One is the parametric set of models, and one is the non-parametric set of models. Okay. So for parametric set of models, you've already seen logistic classifier, or an SVM classifier. For a non-parametric classifier, you've already seen k nearest neighbors, right? So how many of you have not seen KNNs? Okay, and multi-class logistic regression. Sorry, classification. Okay. So we're going to focus on parametric models because most of your deep networks are going to be parametric, families are going to belong to parametric families. So in parametric models, a fixed set of parameters and hyperparameters pretty much determine your model. And once your model is determined, you kind of use it in production or in with test images or test data. Okay. So we'll pick a concrete parametric model, I'm going to represent that model using two parameters. So my parametric model is going to be just this function f, which takes my feature vector x and has two parameters, w and b. And so let's assume that my input is a d-dimensional vector. So if I have an image which is a three-dimensional array, either I can apply all the feature filters or the filters that I was talking about in the previous slide to create histogram of colors, histogram of oriented gradients, and so on. Those are going to be vectors. I can just concatenate them and create this d-dimensional vector. It's going to be huge, potentially 1,000 dimensional. It's going to be maybe 10,000 dimensional, but okay, some finite dimensional vector. Okay. Or very naively, what you can do is just you have a this three-dimensional array of an image. You can just vectorize it. So you know the vec operation in MATLAB or something like that. So you just concatenate row by row by row till you kind of make it into a vector. Okay. So W is going to be a parameter which is going to be P cross D dimensional, and B is also going to be a parameter which is going to be P cross one dimensional. So in particular, we're going to pick, to start, let's pick a model which is just going to be a linear model. So f of x comma the parameters is going to be w times x plus b. Okay. So w is a matrix. Okay. I don't know if you've seen some other classical treatments of, for example, linear classifiers. You might have seen that w is a vector, right? So we are going to be looking at multi-class classification, and so there we will have a matrix as a parameter rather than a vector as a parameter. Okay. If it was binary logistic classification, then w would be, for example, a vector. Okay. So we're going to fix a linear model right now, and we're going to move to potentially a non-linear model. In fact, you'll see that feed-forward neural networks are an example of a non-linear model. So we'll get to the non-linear models later. Okay. So for now, we have this parametric model. So given the model, our classifier can be as follows. These are some of the choices that you can make. So you can so let's say it's a fixed pair. You've already set the W and B for your model. So your model is completely specified. So given that model, your classifier is just going to be, okay, I have this model is going to output a p-dimensional vector because I have p classes, which I did not mention here, but I have p classes or p categories or p labels, and my model is going to return a p numbers, right? Let me call these scores, and so my classifier is just going to be the index of the score vector, whichever is the maximum. Okay. So that's my classifier. Or I can kind of also do something else. I have the score vector, which are a bunch of numbers which I got from the model wx plus b, right? P-dimensional score vector. I can somehow transform them into probabilities by somehow normalizing, and then I can pick the index with the highest probability. So when the second point is just saying that I can probably normalize the scores in some way, and then still pick the index with the highest probability. Okay. Yeah. What is W1? So those are the parameters of a model. So when I said, I said models are parametric or non-parametric, right? Like if you think of k nearest neighbor, you can think of k as a parameter, but I would call it a hyperparameter. So nearest neighbor doesn't have any parameters. You just index all your training data. Okay, it's basically. So when you want to specify a model, you will have to specify the parameters pertaining to the model. So when I said when I say when I say f is the model will have the data part or the variable part and the fixed part. The fixed part is the parameters. So okay, is it clear or you're still confused? So if you look at this expression f of x comma w comma b, okay, instead of w comma b, forget b, because b and w are basically the same thing, so you can ignore b for now for this discussion. So you have two parts. F has two arguments, right? X and let's say w. Okay, b is the same as w, so I'm ignoring it. Now x is going to be the input for this function, which I'll get these inputs either at training time or test time. So x is going to be typically the feature vector. Now, what is this function? How well, when I just write a symbol f, how is it? Is it sine of x, or is it x square? Is it something else? You have to specify some other thing to kind of pin that function down, right? So that is characterized by w. Yeah, weights are also parameters. In logistic regression, the W that you've seen is a parameter. In SVMs, W is a parameter. Yeah. Do you have? So it's clear, right, what parameter is and what is not a parameter is typically going to be the input at test time, okay, which is going to be your test image, and whatever is not your input but still specifies how the model looks like, whether it's a linear model or a nonlinear model, is going to be the parameter. So when you see this, it's a linear model because it's linear in x. Okay, right? If there was some w times x plus w prime times x square or something, it's not a linear model. It's probably a second order model or something like that. So the linear model is determined by a fixed value w and fixed value b. As you said, for neural networks, it's going to be the weights of the the layers. Okay. So I just said. So first of all, also note that this f function, I'll have to, I guess, recap it. But the f function is actually a multi-output. It's a multi-output function. The output of f is a p-dimensional vector, which is what I'm calling a score. Okay. So given these scores, I can pick the coordinate with the highest score and call that as the label. Basically, the index of that score to be the label. That completely specifies this linear model business, right? So I said we have been given a fixed w and b, but the whole point of machine learning is going to be to figure out a really good choice for w and b. So once you are restricted to a particular model class or a family of models, let's say linear models, where w and b are not fixed, I just want to fix that w, fix that b, such that when I fix that w and b, it's a fully specified model. Once I use that at test time, it really does good classification, right? So how do I fix that? So for that, I need to kind of come up with a notion of what is a good w, what is a good b, what is a good parameter. And the second thing I need to do is, okay, if I know what is roughly I can specify indirectly what is a good w or a b, how do I get to that w or b? Because nobody is going to hand me that w or b. So I'll have to find it, and for that I'll have to use optimization. Okay. How many of you have done any course on optimization? Just checking. Linear programming or convex optimization or something like that. Okay, we will not need any background, but I'm just trying to get an idea of how many of you have seen optimization as a tool in some other course. It need not be an optimization course, but you might have seen something related to optimization, right? Okay. So let's look at the first part, which is going to be specifying what is best. Okay, so that's you have to we'll try to specify what is best using what is the notion of loss functions. Okay, so let's call the jth coordinate of this model as sj. Okay, it's going to be the score of the jth coordinate. I said initially that we'll have a bunch of labels, right? I said we'll have p labels. So j is going to be a number, j is going to be an integer which is going to be going from 1 to p, right? So the jth coordinate of f is going to be sj. Let L data be a function which I'm going to define. It's a function defined on what is called training data. So training data is a specific jargon. We'll get to that later as well. You might have already known. You might already know what it is. So I'm going to specify first something called L data. Okay, it's a function. Now I'm going to choose this function as a decomposable function over n terms. You remember what n is? N is the number of training examples. Okay. So when I say it's a decomposable function over n terms, I'm just saying that I'll have one one function defined on one example, another function defined on another example, so on for all the n examples, and I'm gonna somehow compose L data as a composition of these separate functions. Okay. In fact, it's not that complicated. In fact, it's just a very simple thing. I'm gonna define L data as a sum of n terms, where each term is another function Li, okay, which is specific to an example. So I have n examples, n training data. Each one is an example. I'm going to define one function Li for each example. Okay, and it's going to be the same function for all the examples. So let's look at this point, which is. Can you see the pointer? Okay. Okay. Let's look at first loss function. Okay, it's called the logistic loss, or it's also called the cross entropy loss or the softmax loss. And for an example I, so remember I is a number which indexes the example, so it's going from 1 to n. Okay, there it can take all these values. For a fixed I, I'm going to define Li to be the negative of the log of this conditional probability. Okay, where the conditional probability, if you kind of ignore that it is a conditional probability, it's just a function like this. It's e to the power sj divided by the sum of all e to the power sk's. Okay. So remember, sj is just the jth coordinate of my model's output. The range of this f is f outputs p-dimensional vector, right? So the jth coordinate is sj. So this conditional probability that the class or the label is j given my feature x is going to be just e to the power sj divided by sum over k of e to the power sk. So what is the sum over? The sum is going to be over what is it going to be over? It's a very simple question. All the? Yeah, its k is just going to be from 1 to p. Okay, there are only p terms. P scores are there, right? I mean, I said j is the coordinate. I just use k because I use j at the numerator. That's all. So I have p scores or p integers or whatever, p real numbers. It doesn't have to be integers. I'm just gonna sum e to the power those numbers. Okay, that's gonna be the denominator. It's a fixed number, and for every j, I can define this conditional probability by just taking the numerator e to the power sj divided by this. This you might have seen before in your data mining class. It's just a softmax function. Okay. So the loss for the ith example is just the negative log of this fraction. Okay. And the loss over my whole training data, which has n examples, is just going to be the sum over each example of this definition. So let's say I was given a model which has this value, which has a fixed value w and fixed value b. Then for every training example that I have, I can compute this course, right? And I also know if I can compute this course, I can compute the loss for each of these examples by it's a simple transformation, right? I compute these scores which are p-dimensional. I'm gonna pick that score which is actually relevant to that example. So the example is defined by two parts, a feature vector and a label, right? So xi and yi are the two parts of the example. So I'm gonna pick only the yith coordinate of the score in the numerator. So if you look at the loss is only a function of what was the score that you what was this conditional probability, which is a function of the scores that you assigned for the yi'th coordinate. Okay. So I just wrote this expression for any j. Instead of j, you substitute yi. That's all, right? So your model outputs a bunch of scores. You can compute this derived function for every index j, but I'm going to only plug in that index, which is the actual label for that example, and I'm going to account for li. I'm going to just define li like that, and I'm going to define L data as just a sum of all these li's. Okay, this you've already seen, so I hope I'm not belaboring the point. Okay, so you've seen. Okay, let's look at a slightly simpler loss function, which is called the SVM loss. Okay, multi-class SVM loss. So here the loss for it's again per example. So loss for the ith example is just going to be the max of 0 or the difference between scores plus a constant. So difference between what scores? The difference between every score j and the right score that you and the score that you got for the right label. So okay, next. So let's say the right label was the first index. Okay, then I'm going to fix SYI to be the first coordinate of my output, right? So f is going to have, let's say, 10 numbers. I have 10 classes. The first class is a true class for this ith example. Let's say the first class corresponds to, let's say, a laptop. Then that's a true class. Then I'm going to fix this number as the score that my model obtained for the first, in the first coordinate. I'm going to fix that number, and then I'm going to look at all the other numbers except that first coordinate. So I'm going to sum over 9 other terms, right? I have 9 other coordinates which are not the label for this example, and I'm just going to add this. I'm just going to add over this particular function. It's just called a RAM function. Yeah, it's just called a RAM function. It's just a max. It's a thresholding operation. If your difference, if your second term is negative, then just pick 0. If your second term is positive, just pick that number. Okay. So these are 2 losses that you might have seen before in your previous class. So that's why I'm trying to not explain them in a lot of detail.
Why do you have a C?
C is there for an interesting reason. If you don't have a C, then you can scale the scores actually. So to make it scale non-invariant, you put a C there. Scale as in what? Let's say I have Sj, and I got the scores by which are the coordinates of the output of the f function, right? If I multiply all the scores by 10, it's not going to change anything, right? Unless if there is no C, if I multiply it by 10 or something, it's not going to change the answer, right?
In the SVM loss, the summation.
Yeah.
So you're going from all the classes from 0 to all the classes as compared to J, right? J is a parameter which is moving from in between all the classes.
Let's say we have 10 classes. Okay. We have laptop and everything else. It's 9 other classes. I'm not going to index. I'm not going to describe, but let's say there are 10 classes. Then this summation is going to, let's say for this example I, the true class is laptop, which is in the first coordinate. Let's say yi is equal to 1 means laptop. Yi is equal to, let's say 10 something is something else. Yi is equal to 2 is something else. Okay. For this ith example, yi was it's an image of a laptop. So I know the true label is a laptop. So I know that the first coordinate score is what should be higher than everything else. Intuitively, that's what I should have, right?
But why is not the true class included in that summation?
No, you can include it, but it's going to be 0. Right? I mean, not 0, but C is a positive number, so it's going to be a constant, which doesn't matter. I mean, in loss, whether you have a, if I add a constant like a plus 10 to all these functions, it doesn't matter. Something like that. Right? So this is a second order, reasoning that you need to think about. But intuitively, what's happening here? Let's focus on this particular loss, right? I said we have 10 classes, and in this for ith example, it's an image of a laptop, and so the class label is a laptop, and let's say the first of the 10 classes is the laptop class. Okay, then I just want to ensure. So this loss is supposed to capture the intuitive idea that my model is supposed to score in the first the model is gonna output 10-dimensional vector, this, in which the first coordinate should be the highest because it's a score, right? So you should score the laptop coordinate higher than everything else. If that was true, then this loss would be 0, because this term is higher than all these other terms. Modulus is constant, then your loss should be 0. In the sense, you're not penalized for getting the right answer. But if it just so happened that, let's say, the second coordinate was bag, okay, and the score for bag by my model was higher than the laptop, then I should get penalized, and that's what is happening with this particular example. Is that clear? Okay. So that's the reason why I put that as L subscript data, or the loss for the training data, is because there's another thing that you might have encountered before, which is called regularization. Okay. So what is the need for regularization? There are various points of view that the community has taken to kind of justify regularization. For example, sometimes the loss function is not a nice function, in the sense there is no single optimum model there. Like there could be a W1 B1 and there could also be a W2 B2, which both lead to the same loss value. So in that case, you don't know which model is the right one, because we both get to the same number, right? And the second point of view is that I may have certain prior knowledge that I like certain types of models. What do I mean by that? As I said, model is specified in this running example by W and B. Let's ignore B. Let's say my prior is that W should look like a diagonal matrix. Okay, so that's my additional knowledge that I'm bringing in, which is not present in the data. The data is just my n examples. But if I bring in additional knowledge that W should look like a diagonal, then that is my desired, my additional knowledge is saying W should look like a diagonal. Data is going to say something, about how W should look like based on L data. I need to balance those two. So to incorporate my desired properties on the model, I can bring in regularization. And the third thing, which also people talk about, is controlling what is called overfitting. So maybe for linear models it doesn't make too much of a sense, but for example, you have polynomial models, okay? Which means that you're fitting all sorts of higher order polynomials to your data. In that case, if you have n, let's say in one dimensions, if you have n points, xi yi pairs. Let's say in one dimension, what do I mean is x is one dimensional and y is one dimensional. If you had xi yi pairs, n of them, you can fit a polynomial. If you had enough degrees of freedom, which is precisely I think n plus 1, you can fit a polynomial which passes through all the yi values in regression. But if you restrict your polynomial to be a second order polynomial, it's gonna not fit exactly. There's gonna be some error. Not all yi's will fall on the curve. So something like that. So those are the few points of view which kind of try to motivate why regularization is needed, and so typically what you'll see in machine learning is people don't just define loss or define loss function as just a function of the data, but they'll also add what is called this regularization function. Okay, I've represented it as R of W comma B. In this case, W comma B, just because I have two parameters, I'm explicitly stating them. But you could think of just W or theta or something to represent the parametric model. Okay, and so now just because I added a regularizer, I also added an additional parameter. Do you see that? Yeah, that's the additional parameter, and by definition or subjectively, I'm going to call it a hyperparameter. Okay. There is nothing which defines it as an hyperparameter. It is also a parameter of something that I'm going to tweak in this classification task, while getting my model. So my final loss is going to be L data plus lambda times R of W comma B. So for any given model W comma B, this and a given data set, n data, these n examples, I can compute this L, okay, and this L is going to be a single number which is going to score how well this model kind of fits my data, right? I think here in the last bullet point, I'm trying to motivate why do you need a regularizer for the SVM loss, because if you just look at SVM loss, let's say there is a model W0 B0 such that L data is 0, okay. What do I mean by L data is 0? You remember L data is the sum of n terms, okay. If L data is 0, then my first claim is that all the LIs are 0. Is that true? Okay, it is true because firstly you will have to notice that LIs are actually non-negative functions, in the sense they're lower bounded by 0. If you look at the SVM loss, if this is positive, this is picked up. If this is not positive, 0 is picked up. So it's never going to go negative. Okay. Similarly, for logistic loss, this since it's a normalized number, whatever this number is inside, what is this? This huge expression is just a placement for this normalized number, right? E to the power sk divided by some more k e to the power sk. So that number is always going to be less than 1, less than or equal to 1. Okay, that is fine, right? Because of the normalization. So if this is going to be less than 1, then the negative log of that number is always going to be positive. Okay. Log of anything log of 1 or something less than 1 is going to be negative, and negative times negative is positive. So these LIs or L data is lower bounded by 0. Okay. But when I say there is a model such that L data is 0, which means that which means that each of the LIs is 0, and let me pick a number alpha which is greater than 1. Then what you will see is that alpha times W and alpha times B also satisfy L data is equal to 0. That you can see very easily, right? If it is going to be 0, if I kind of increase the score and increase that score, it's not gonna. One second, I'm getting confused. Oh yeah, the C is causing an issue, but okay, I think let me scratch this example because it's not clear. Yeah, anyway, what I'm trying to say is that there will be multiple models potentially if you don't have a regularizer. That's what I'm trying to say. In this case, because of the CL, we'll have to reason it a bit more carefully, which I don't want to do on the fly. So let's move forward. So ultimately, these slides are trying to convey that you need both the function of the training data and a separate term, which is just going to be your prior knowledge incorporated in the regularizer term. Okay, and RW. So this regularizer can be just a function of some subset of it can be just a function of a subset of your parameters, or can be a function of all the parameters. So, for example, here in these examples that I've shown, what is popularly called an L2 regularization, I'm just regularizing the first parameter, let's say the matrix itself. So in fact, for the matrix there is a specific definition of what it means to have a 2 norm square, but let's think of it as what is called a Frobenius norm, which is just I have a matrix, I just pick every element, I just square those numbers and then just add them up. Okay, that's the Frobenius norm. But that's the regularizer. So what does this regularizer convey? It's trying to say that okay, you may have potentially many models that you can pick from, which all kind of do well on the L data function. They all look very similar. But among all those models, I want to pick that model, as in that W, which has a lower Frobenius norm, which just means that the W matrix kind of spread out. There's no one large term, because these are all because this term kind of represents the sum of the squares of the individual elements of the matrix. One term being huge means the square of that number is going to be very huge, and so that model is less preferred, because we're going to be penalizing for a spike in that matrix, basically. L1 norm is basically trying to say that I want somewhat of a sparse matrix. Okay, I mean intuitively it's trying to say that it's trying to kind of if I have a multiple choice of models which all have the same L data part, same loss on the training data, I want to pick that model which has a slightly less number of non-zero elements. Okay, if I have the option of two W's and one has lesser non-zero elements, then I'll pick that because that will have a lesser L1 norm. Okay, that's the intuition between these regularizers, and a convex combination of them. By a convex combination, I just mean that you just put a positive number here, which is between 0 to 1, and you put a 1 minus that as the second coefficient, and so this is what is called a convex combination, and that's called the elastic net regularizer. Okay. Regularization need not always be explicit as well, and so there's a particular type of regularization that will come up in deep learning called dropout, and we'll see that later. Okay. So that covers loss functions and regularizers. So before we get to optimization, let's look at the landscape again. We described a few things, right? We described first the data. These are the n examples. Okay. We described a model. In this case, we were thinking of a linear model, but it can be any model. Okay. F of x comma parameters can be anything. It can be a polynomial. It can be a neural network. It can be anything. So, but for now, let's think of it as a linear model. Okay. From the parameters, I can define my preference, which is independent of the data, which is going to be captured in the regularizer. Using the parameter and the feature vectors of the data, I can define this score function or the model, which will give scores to each of my, let's say, 10 classes or whatever it is. And because I know the ground truth, the true labels, I can use the scores and the ground truth to define the final loss, okay, L, which is going to be L data plus the plus gamma times the regularizer. Okay. Yeah.
In the last slide, that RWB is the whole expression.
RWB is gonna, yeah, it can be a function of W or B or both. So here I'm saying that RWB is just Frobenius norm. Is there an issue? Yeah.
No, I mean RWB is L2 or L1 or that whole expression.
It can be any of these. Any function. You can pick any function of just the parameters and ignore the data basically. So you can pick a constant function, which means it's irrelevant. There is no regularization. But here I'm just saying that I prefer models with lower Frobenius norm or something like that. Yeah, so these are just examples in case you didn't follow. And there is another type of regularization that we'll see later. Okay. So we'll get to optimization, which is actually kind of a key topic that we'll kind of revisit multiple times in future lectures. There are many ways to optimize, and what we will focus on is what is called the family of first order methods. And the key ingredient in this family of methods is called what is called a gradient. Okay. How many of you remember Taylor expansion? Okay, so if you do a Taylor expansion for a one-dimensional function, the first term that you have will have a derivative, right? So just the higher order kind of analogous object is the gradient. Okay. So there are other well-known optimizations. So if you just think of from the point of view of optimization, forget about machine learning. There are many other methods which also exist to optimize any objective. Okay, and for example, there is second order methods which use second order information about where they are in the objective landscape to kind of move towards the optimum, whether it's a maximization problem or a minimization problem. So here we're going to just focus on first order methods, and one of the methods that you might have heard of offhand is called stochastic gradient descent. Okay, so we'll get to stochastic gradient descent soon. So that's a part of this family of first order methods. Okay. roughly speaking, first order methods are kind of worse off than second order methods and so on. But at the same time, they may offer computational, benefits that you will not see, and stability benefits and so on that you will not see with higher order methods, okay, and more complicated methods. Okay, so gradient is just a vector of partial derivatives of a function, okay, and it can be computed numerically. Let's say if the function is one dimensional and you want to find the gradient or the derivative at point z, then you can just kind of add a delta to z or add a h to the z, evaluate that number, and take the difference of those numbers and divide by the delta that you added, okay, and h is, let's say, positive. So numerically you can compute the gradient at any given point. Analytically also you can compute the derivative, right? If you had an analytic formula, then you can use calculus to chain rule to kind of derive what is the derivative at any given general point, okay? So we're going to now focus on an example optimization method of what is called as batch gradient descent, okay? So remember what is our objective here. Our objective is, we kind of defined what is the best, we kind of fixed our models, which are going to be, for example, linear models parameterized with W and D. We kind of fixed what is called which model is best by defining this loss function, which is going to be part data, part regularizer, but it's going to kind of quantify which W comma B pair is good or bad. So a W comma B pair is going to be good if L is going to be low, right? So that's the objective that we've already defined. Now with that objective, we want to get to a good W and B given a random W and B. Because we don't know what is the right model for our classification task, we start with some W and B which we kind of randomly initialize, and hopefully these optimization tools, for example batch gradient descent, will let us move towards that W comma B pair which is going to be best in terms of that loss function, okay? Let's say the SVM multiclass loss or the logistic loss. Let's parse this method in chunks. So what is meant by batched? Batched just means this optimization method, which is gonna make us get to the good W comma B pair, is gonna use a bunch of examples rather than one example at a time. That's all it means. So there's something called AlexNet. So remember at the very beginning I said in the ImageNet large scale visual recognition challenge there was a 10% drop, 10% improvement in classification performance. That particular neural network or deep learning architecture was called AlexNet, and it used 256 examples in one batch, okay? So that's all it means. So batched is not very critical for understanding at this point of time, so let's ignore that. Now gradient descent. So gradient descent is a very key algorithm in a lot of in the class of first order methods, which is used in machine learning, out of machine learning, and a lot of other areas. So, and the concept is very simple. You get the gradient of the objective, in this case that was L, right, with respect to the parameters that you want to kind of optimize for, right? We want to ultimately get the best W and B, right? So we want to get the gradient of the objective, which is L, with respect to W and B, and then we're going to just update our current set of W and B. So gradient descent is an iterative algorithm. So we're going to start with a W comma B pair. We don't know whether it's good or not, okay? I can evaluate the gradient of my objective, which is the L, at this point, okay? And then I'll move, as in get another candidate W comma B pair by moving in the negative direction of the gradient. That's what it means that's what we mean by gradient descent, okay? When I say the negative direction, all I'm saying is I have a W comma B pair, which is my current candidate. I found the gradient of L with respect to W and B, which I'm representing as this grad of L with respect to W and grad of L with respect to B. Okay, those are two vectors potentially. Actually, this is going to be a matrix and this is going to be a vector, because W is a matrix and B is a vector. And I'm gonna just nudge them or change them, and I'm gonna come up with a new candidate of w comma b. That's it. That's the iterative algorithm. At any given point of time, I have a candidate. I'll find the gradients, and then I'll just do this simple addition or whatever subtraction and get to the next candidate. Okay. Of course this update step has additional parameters alpha and beta. These are what are called step sizes or learning rates, and we'll figure out how to choose them later on. So for now, just get the gist of the algorithm. What is batched gradient descent? Batched is some concept related to trying to use multiple examples while updating your W and B. So let's ignore the batched part for now. But gradient descent, all it does is I have a current candidate of parameter W comma B pair, for example. I'll find the gradients at W comma B, right? Gradients are going to be these objects. For example, it will be a matrix, it will be a vector, whatever. I'll use those gradients, which are symbolically notated as grad L with respect to W, grad L with respect to B, and I'm going to update my candidate to get to the next candidate. That's all. Okay, and it just works. It works as in for convex problems with this update for appropriate choices of alpha and beta, you will get to the global optima. Okay, that's what I mean. So I just wanted to kind of concretize one algorithm to update W comma B, but we also have an additional parameter. Once we added the regularizer, we had that lambda parameter, right, which came up additionally. So tuning, so I called it the hyperparameter. So we'll have to tune that as well. Okay, so for that, not just for that, in fact, for the whole classification task, first and foremost, zeroth order thing that you need to do is break your data set into test and train. Okay, which means if you had 100 examples, probably you want to set aside 30 or 20 examples aside and call them test, and you'll never test them, as in maybe you'll test them once a month or once a year when you want just a feedback on how well you're doing in reality, but you'll not take feedback from that set as much as possible. Okay, and then the remaining set, which you have the train set, is the actual set that we were talking about all along, which had the n examples. Okay, to tune the hyperparameter, typically what's done is what is known as cross validation. How many of you have already seen cross validation in one of your previous courses? Okay, so cross validation is a very interesting trick, but in addition to cross validation, what you actually do to tune your hyperparameter, this lambda parameter, is actually what is very naive. It's actually what you're doing is complete grid search, or what is called a grid search or an exhaustive search. So I don't know if you have trained any machine learning or classification model before. For example, if I had a single parameter lambda, it's a scalar, right? So I'm gonna vary that lambda over, let's say, 10 different numbers, maybe in log scale or linear scale, and for each number I'm gonna compute. I'm gonna solve my optimization problem to get to the best model. So for each number there will be a best model and an appropriate loss value, and I'm just gonna pick the loss which is the lowest, and that lambda is gonna be my final lambda. Okay, so it's a very naive search. It's really no optimization going on. But cross validation is something that you kind of couple with hyperparameter tuning. So what is cross validation? If you have your training data, for example, in this example, I've split the training data into four blocks. So let's say my n was 400. Okay, then I'm gonna split that 400 examples into 4 blocks of 100 each. I'm gonna keep 100 examples as this held out block. Each of these blocks, I'm gonna call them folds. I'm gonna hold one fold fixed. I'm gonna use the remaining folds to train, as in do my optimize for the best model possible, the W comma B pair, and then I'm gonna check how the W comma B pair is gonna perform on the last fold, and I can do this in a cyclic order just to get a nicer estimate of how this good how good this W comma B pair is in real life. Okay, it's a cross validation is just a proxy for how well would you do in real life, as in with the test data or with other examples. Okay, So those are the two parts of optimization. One is you actually optimize W comma B, and you also optimize your hyperparameters. Typically, hyperparameter optimization, you pretty much exhaustively search for a good hyperparameter. So it's a very naive search procedure, optimization procedure. Yeah.
Why do you need to remove the test data before classification?
Before doing anything, you need to remove test data.
Yes, but
Yeah.
just for the hyperparameter specifically, or like generally?
No. So actually, I should have the first bullet point. First two bullet points are not related to optimization. It's for the whole classification task. You just need to remove your test data, give it to your manager, and ask them not to give it back to you at all. Maybe for your yearly performance review, they can give it back and see how your model performs or something like that. Yeah. Somebody had a question in the back. Okay. Okay. So that's what. So we kind of touched the major blocks in a typical classification task. We kind of described, there could be nuances with the data, there could be nuances with the model. There's some choices that you need to take with respect to the loss, and there are choices which you'll have to take for what type of optimization you're going to do. And so that kind of is the complete classification pipeline. So next we're going to jump into optimization a little bit more and kind of focus on what is called backpropagation. How many of you have not heard of backpropagation? Okay. So the remaining people everybody already knows what backpropagation is. Okay. But we're going to go through examples. We're going to go through examples and kind of understand backpropagation. There are many resources on the internet which kind of describe backpropagation, but we're going to focus on a very local view, which is kind of very simple, and we're going to kind of not look at the global view, which is very messy while discussing backpropagation. Okay, so backpropagation has just two kind of important objects. Yeah. Okay. We'll have a break of 2 minutes. In the meantime, if you have any questions that you did not understand, you can come forward and ask me.
The thing before, I know that you are saying that it cancels out, right?
No, I was just trying to see. Okay, under the assumption that W naught B naught lead to 0, which means that this is negative, right?
Yeah. So it comes out to 0, the loss function.
Yeah, Li is 0, which
Yeah.
means that this whole term is. Oh my god. Okay, that's why the pluses are there. Okay, anyway.
I think this is on. You're trying to set the thing. Is that how it is?
I don't know. This is just the same thing as that.
No, it's like calibration. For calibration purpose, this comes out, right, normally.
Okay, I don't know, but it's okay. Let's not forget about it. So this term is negative, right?
Yeah.
For W naught B naught.
Mm-hmm.
Now I'm just saying that if you scale
If you multiply
W
by
naught
alpha,
B naught
you'll
with
still get
alpha,
it.
you'll still be negative.
Yeah.
Is that obvious?
Yeah, that's
Okay, then there's nothing else going on. Right? This whole term is negative. I'm just increasing.
This is going to be multiplied. This is going to be alpha sj and alpha s. That's it, right? And it's going to
Yeah.
cancel out.
It's going to cancel out, but the important thing is that it still has to remain negative. That's all.
Yeah.
If you just scale, for example, if this term is positive, this term is positive, which means this term is negative, right?
Oh, okay. I think I get it. Because now
You can't just
C
randomly
depends
scale it.
on- Yeah, it depends on C also.
Yeah, but you can scale it. Maybe within a range you can scale it, something like that. Yeah, that's why C was causing an issue. That's why I said let's discuss it later. Yeah.
Some questions.
Yeah.
So tonight you have your office hours.
Oh, I changed it because I don't have access to my office. So if you have questions, you can just ask me right here.
After the class,
Yeah, here.
there was something confidential that's
Oh, okay, okay. You can ask me here because I don't have access to UH. I'm still working on my access card right now.
so after the class.
So you can just ask me here.
Professor, why did you say that the image is a three-dimensional form? I mean, I see it only as zeros and ones where you have maybe if it's a black and white image, then one you classify as white and zero as black. I mean,
Oh, it's a black and white, yeah, but it has colors, right? So clearly it's
I mean,
just not
are you
zeros.
saying it as 3D? I did
No,
say
no.
three-dimensional.
Okay, let's look at it from a grayscale image, right? Black and white image. You say zeros and ones, right? That's just two-dimensional. It's just a matrix. Now you want grayscale image, so you want a number between 0 and 1 because you want a color gray as well. Let's say.
Okay, so the shades you are assigning as a different dimension.
No. Grayscale is still two-dimensional, but it's not just 0 and 1. It can be any number between 0 and 1. Not just two numbers 0 and 1. It can be also 0.5, it can be 0.7.
Okay.
Then it's a grayscale image.
So,
But these images have other colors as well, right? So that's why you can think of it as three two-dimensional matrices. That's why I said three-dimensional array. I said a three-dimensional array because you need three matrices next to each other. Potentially one looking for red, one looking for green, one looking for blue. Yeah. So once you kind of merge those three, you will get these colors.
so we have three two-dimensional arrays. Is it?
Yeah, two-dimensional arrays. Whether it's 3 or 10, it doesn't matter. But it's ultimately gonna give you a higher dimensional array, right? It's not gonna be a matrix anymore. It's gonna be a tensor. So that's all I said. Okay. You have questions or?
So,
Yeah.
in the previous slide, you spoke about highest scores, right?
Yeah. Oh, okay.
Yeah. So, how do you calculate the highest score? What do you say is the highest score?
Argmax. Oh man, it's pluses are.
Okay.
Yeah, you have 10 numbers, take the maximum. Index of the maximum.
Okay.
You have 10 scores, right? So F is a multi-input, multi-output function.
Okay.
So it will output 10 numbers. Those are the 10 scores. The one of the indices will be the maximum. It's a finite set of numbers. Then one of them number will be highest number, right?
Okay.
At least one of them. It
Okay.
can be more.
So,
but
if this was trying to classify a bunch of images,
yeah.
right?
Given an image, it's gonna give a score for whether this image is a laptop, whether this image is a bag, whether this image. So these 10 numbers will be there. Hopefully, if it is a laptop, the laptop's coordinate score is higher. That's all.
Okay. Oh, okay. So when you're comparing, so when you have a test image and you want to find out whether it's a laptop or whether it's a phone,
Yeah.
right? You already know what is the feature for a laptop, and are you comparing the feature of the test image with
So
the
you
laptop's
generally
feature?
should have a range of values, right, for a laptop because
No, laptop is completely captured in the X vector,
Yes.
right?
The feature vector.
Yeah, whatever is the features for the laptop. Now all W comma B is doing is, or whatever the function is doing is map that feature to a score for whether this was the laptop score is high or something else is high or something else is high.
You would only want to find out if something is high when
Yeah.
when you're comparing a test image, right? So when you have
Yeah, I mean whatever image. So this is just a fixed block, right? If you give me an image, it will tell me a score for each of the labels.
Oh, okay,
Yeah.
okay.
so then based on whichever is the highest, you map it to that particular image, is it?
No, whichever is the highest, you ideally want this mapper to be such that it gives me a laptop score
Correct.
to be the highest. That's all.
Okay.
We can discuss again at 8:30.
I would like to update the class.
Okay.
Is it possible or?
It is possible. Yeah, it's fine. You can drop me an email as well.
Okay, I will do it.
Yeah,
now.
yeah,
Okay. Okay, thank you.
Okay. I think it was it's more than 7 minutes. So let's focus back on the key concept for today. You're in a deep learning class, so you need to at least get one concept per day. So the key concept is going to be backpropagation. I don't know how to get rid of this plus sign, so if it's do you know how to get rid of? Clear, but there's one more plus sign. Okay, anyway, I'll explain a way. If it's causing confusion, we'll look at it again. So for the first, to understand backpropagation, so we're going to take a point of view which is more engineering and which is more systems point of view. So we'll introduce one concept which is called a computational graph. Okay, so consider a simple function g, which has three scalar arguments a, b, and c. Okay, and the function is just multiplying a and b and adding c. Okay, that's our function, and so a computational graph represents this computation or these composition of computation. So a and b is going to be multiplied using this multiplication node, and then it's going to be passed on further ahead, and c is going to just add on to it, and the output is going to be towards the right side. Okay, so that's an example of a computational graph. So given that we can represent a function as a computational graph, we're gonna kind of understand what backpropagation is. The intuition is backpropagation is just trying to codify what we already know in calculus, which is the chain rule. So let's look at the same function from before. Let's call the intermediate computation as output of the intermediate computation as h. So the output here is going to be, I'm just labeling it as h. Okay, and then the actual function g is going to be h plus c, right? So g is going to be h plus c. So we're gonna, as the name backpropagation implies, we're gonna propagate something backwards. What is that something? It's gonna be gradients. Okay, so let's define, or actually this is true, but we're gonna first pick the gradient of the output with respect to itself. The output, the final output of this computation is g. So g, the gradient of g with itself is just 1. Okay, and then we're also gonna compute at this node the gradients of its output with respect to its inputs. Okay, so this was the function, which is this plus circle node here, is g is equal to h plus c. So what is the gradient of g with respect to h? 1. Yeah, so gradient of g with respect to h is 1, and gradient of g with respect to c is 1. It's a symmetric function. Okay, so we're gonna compute at this node these gradients. Okay, and then we're gonna also compute, and then we're gonna let's hold on to the propagation bit for now. Let's look at the next node. There are only 2 nodes in this computational graph. Let's look at the next node. H is a product of a and b. So let's look at the local gradients. The gradient of h with respect to its input. So there are 2 inputs for h, right? For this node, which is computing h as an output. So gradient of h with respect to first input a is going to be the second input b, and the gradient of h with respect to its second input b is going to be the first input a. Okay, those are the local gradients. So this part, we just focus on this part and said h, h is the output here. Its local gradients are these 2, and g is the output here, and the local gradients are these 2. And let's say since this is the final computation, I just define, I just said gradient of g with respect to itself is 1. That's fine. So what we want to ultimately do, what we want to ultimately do, we said this is the function, this is the computational graph. What we want is the function's gradients with respect to its inputs. Okay. So what do I mean by the function's gradients with respect to inputs? I just mean I want the gradient of g with respect to a, with respect to b, with respect to c. That's the output I want for any given function. In this case, this running example, I'm taking this particular function. So given any function g, I want its gradients with respect to its inputs. Okay. and in this case I want the gradient of G with respect to A, gradient of G with respect to B, gradient of G with respect to C. Okay. On this slide, I just did some local calculations. I said, okay, I'll get to the gradients of G with respect to the inputs later. Let me focus on gradients of, for example, G with respect to its own inputs. I define an intermediate input H, so I know the local gradients here, I know the local gradients there. The assertion is that we can find the gradients of G with respect to input by simple chain rule. Okay, how is that? At this point, I started from here. Okay, I saw, okay, this is the G node and I know its local gradients. Let me pass this local gradients back through the preceding nodes. Okay, let's look at the lowest. Let's look at input C. G is already the local gradient of G with respect to its input is already telling me the gradient of G with respect to the input C. So gradient of G with respect to C I already know because it's a very there's no other computation block preceding G. Okay, that's, I said, again to recap, my objective was to get the gradients of G with respect to all its inputs. So gradient of G with respect to C is 1 and there's nothing happening. So I have already computed one of my answers. Okay, let's focus on the top part. I want to get gradient of G with respect to A. Okay, but I know the gradient of G with respect to H here because I locally computed it here. I know the gradient of H with respect to A because I locally computed it here. The gradient of G with respect to A is gonna be a product of these two. If I can pass this gradient over here back through this node, then I can find the gradient of G with respect to A because, roughly speaking, the gradient of H kind of cancels. Okay, that's pretty much what chain rule is in calculus. So I can compute the gradient of G with respect to A. It is actually equal to B, and I can compute the gradient of G with respect to B, which is actually equal to A because it's the product of 1 times A and 1 times B respectively. Is that clear? At least for this simple function, you can actually just directly see, right? I mean, you can see what is the gradient of G with respect to A. The only coefficient of A is B, so gradient of G with respect to A is B, and that's what we kind of pedantically saw it here. But let's generalize this. The plus sign is occluding gradient of H with respect to A. So I'm just showing you the same thing as before, where now I have kind of dropped that the specific function that we were looking at. We have dropped that. We were looking at A plus B times A times B plus C, right? So let's ignore that. Let's say we have a generic block. Let's focus on one block. We had a H block here, right, which was a multiplication here. Let's ignore multiplication. Let's say it's some function which has two scalar inputs, A and B. Okay, what that function should do is the following. It should find its local gradient with respect to its inputs. So gradient of H with respect to A and gradient of H with respect to B. If it can compute those two, then this node can pass the gradients from its output to its input to compute the gradient of the output with respect to its input. So what do I mean by that? So gradient of H with respect to A is known here for this local node because it knows what it's computing and it knows its input, right? Let's say somebody from the other side, some other node or somebody gave this node the gradient of some other function. Let's say H is feeding into another function G later on, whatever function that is. If that function could, because that function can again analogously compute the gradient of its output with respect to its input. So its output, let's say, is G and its input is H. That means it can compute gradient of G with respect to H. Let's say since it can compute that, it's passing it back to its predecessor node in the computation graph. If this node can get this gradient information, then it can just use this information and multiply it with its local gradient and then output it back to its inputs. That's all. That's the only thing that's happening. Is that clear? So that's what I meant by local view. If you can draw a computation graph for any computation, let's just focus on one node. Let's say it's a multiplication, let's say it's a more complicated function of multiple inputs, doesn't matter. as long as somebody at the on its succeeding side can pass the gradient, their local gradients to it, then it can pass that local gradient times its local gradient back to its inputs. So let's say H is just so let's say A and B are the actual inputs to this whole computation graph. H is the first node that they encounter. Then we can go all the way from the ultimate output. Let's say G is the ultimate output, which which I have not shown as a circle here. We can find the gradient of G with respect to the input B by just passing the gradient of G with respect to H, which was the G blocks' input, times the gradient of H with respect to B because of chain rule. So you get gradient of G with respect to gradient of B. That's backpropagation in a nutshell. Yeah, I just yeah. So if you get back this from some guy succeeding you, you just multiply it with your local gradient, you get the gradient of whatever G with respect to your input. Okay. And let's say H, the output of this computation block was fed into multiple outputs. Okay. Sorry, multiple subsequent nodes. Then all you have to do is kind of add these two. So maybe some gradient is being passed by a subsequent node. Maybe its function is G1. Another node is outputting G2 but taking H as an input. Then you can find those nodes would have computed local gradients, right? Then they will pass those local gradients. You will add those local gradients and multiply it with this guy's local gradient, output the thing that you want to output. So these are all. So all this is not symbolic actually. So what is really happening is A is taking a particular value, B is taking a particular value. At this node is gonna do that computation, H of A comma B. It's gonna be some number. It's passing on that number to the future to the subsequent nodes as H's. But for those particular values, it's also computing the local gradient, right? For example, if H was a multiplication block, if A is 1 and let's say B is 2, and H was a multiplication block 1 times 2, then the gradient of H with respect to A is actually B. So it has to kind of store the B value, which is 2, right? So these are not symbols. These are actually, once you pass A comma B, at that A comma B point, it can compute the local gradient. Gradient of H with respect to A is going to be B, which is whatever that number is. So, okay. So let's consider, with this point of view, again another example, and this time it's going to be a slightly more complicated function. Okay, so consider this function which has 4 inputs. Okay, this is called the logistic function. Again, you can kind of rewrite if you've done binary logistic classification, you might have seen this function. Okay, again you can think of ax plus by as a scoring function, where I have explicitly written, if it's binary logistic classification, W is not a matrix but a vector. If it's 2-dimensional, then it'll have 2 parts, right? I'm just calling it as A comma B. Then it's A times the first coordinate of your feature plus B times the second coordinate of your feature. So that's what AX plus BY is. But anyway, ignoring that, we have a function which has 4 scalar inputs, A, B, X, Y, and the function computation is 1 by 1 plus e to the power minus products, sum of products, right? So the computation graph will look like this. A is getting multiplied by X at some node, okay, and B is getting multiplied with Y at some node. They're getting added. Let's call this intermediate nodes C, D, and Z, and then Z is getting passed on to this function, which is the logistic function, which is 1 by 1 plus e to the power minus Z, and final output is G. The computational graph is clear, right? Okay, and also the intermediate computations are also clear, right? It's just A times X, B times Y, and so on, right? Those are the ones which I put in brackets. If Z is going to be minus 2, then the final output G is going to be 1 by 1 plus e to the power 2. Okay. Now let's try to find the gradient of G with respect to all its inputs. Okay. So inputs are A, X, B, Y. So we want to find the gradient of G with respect to let's say gradient of g with respect to y at this given point. Gradients are always with respect to, you can of course analytically find some expression for gradients, but we'll find a gradient with respect to the input y or whatever, argument here y at a given point, which is a is equal to 2, b is equal to 1, x is equal to minus 3, and y is equal to 4. Okay. So for that, what we'll do is first compute the local gradient here, the big node here. What is the local gradient? Just to calculus, I mean, if you differentiate this function, you will see that you will basically get this. Okay. I am not doing it on board because the pen's not working. So, so this is the local gradient. Okay. So this node computed its local gradient, and it's gonna. Okay. We just saw what the computation at these points. What g is. G is this. Okay. To get that, we kind of traverse the graph from left to right. Right. We kind of first did the multiplications, then the addition, then the logistic transformation, and got the output. Now we're going to go from right to left. We're going to say, okay, the local gradient of this node, local gradient as in the local gradient of the output with respect to its input at this node, at this current value, which is z is equal to minus 2, is this, right? Now I'm going to just pass this number back to this plus node. At the plus node, the output is z. Let's pick one of the inputs, let's say c. The gradient of z with respect to c is what? No, it's a plus node, so it's just 1. So z is equal to c plus d. Partial derivative of z with respect to c is going to be 1. Partial derivative of z with respect to d is going to be 1. Right? So I know the local gradients of at this node. I have been passed on this number, right? This gradient, but basically this number. So what I'm going to do is, as I said, so the new text address is just this. Gradient of z with respect to c is 1. And so I can find the gradient of g with respect to c as just the product of this 1 times the gradient that was passed on. Right? So I have a local gradient number, which is 1. And I have the previous gradient which my succeeding node had given back to me. That is this. That is this. So gradient of g with respect to c is this number. Okay, I'm going to pass this back to the next node, which is going to be this multiplication node. Before doing that, let's do the bottom part as well. Bottom part is symmetric. Gradient of z with respect to d is 1, and so gradient of g with respect to d is going to be 1 times the gradient which was passed on to me. Right? Let's since from this point onwards it's all symmetric. Let's just focus on one of the inputs. From this point onwards, this is all very symmetric. So let's focus on y. So gradient of output d with respect to its input y, y it's a multiplication node. So gradient of d with respect to y is going to be the opposite argument, the complementary argument, which is b, right? So the local gradient is b, and what was passed on to me is this 1 times e square by 1 plus e square the whole square. So I just multiply those two, and b is actually taking a value 1, and so I just have the same number. So that is the gradient of the final output with respect to this input that we just looking at a computational graph we derived. But we can always derive the same thing using calculus right here. But by doing this, we have kind of reduced this gradient computation for any arbitrary function into just focusing on a computational graph and going from the final output stage wise to the inputs, right? Just focus on the local gradients, get something from the your successor and pass it back to your predecessor. That is the backward propagation of gradients. Okay. So that's nice for scalars, but what happens when you have a vector? Actually, not much changes. So let's say A is now a p-dimensional vector, B is a q-dimensional vector, and output h is a r-dimensional vector. And let's say some subsequent node g, ultimately, for example, we know that in our classification task, the final computation was anyway a scalar, a loss value that we attributed to the model and the input. Anyway, input doesn't change, so it's fine. for a model we attributed a single number scalar, right? So let's assume similarly like some final thing, in this case the node succeeding h is a scalar, okay? Then we'll see that the gradient which is passed back to the node h, because the node h is outputting r numbers instead of one number, the gradient that we're going to get back is actually going to be r dimensional, okay? How we got the r dimensional vector, let's ignore it because we're going to focus on the h node. Let's say we got the r dimensional vector. What is the local gradient of h with respect to its input? We know that h is a some function which has r outputs, and on the a side, a is a p dimensional input, right? So the gradient of h with respect to a is actually a matrix, right? Gradient of the first coordinate of h's output with respect to the gradient of the first coordinate of a's input. Gradient of first coordinate of h's output with respect to gradient of a's second coordinate, and so on. So you'll have a matrix with all these basically dou h by I, dou hi divided by dou a j, something like that, where j indexes each coordinate of a, and let's say I indexes each coordinate of h, which is r in number. So it's going to be for example, it's going to be a p cross r matrix. So what I'm saying is, from the scalar thing that we saw 2 slides ago, nothing much has changed. The local gradients have become matrices, and the inputs could be could be scalars or matrices depending on what the subsequent nodes are, okay? So again, it's the same thing. We multiply this vector with this matrix to output, for example, here a vector which goes back to which goes back to subsequent nodes if available. But let's say a itself is the input, a itself is the input. Then a is a p-dimensional vector. We got back the gradient of the final output, which is a scalar, with respect to a as a p-dimensional vector. So dimensions are matching. One observation to make. Okay. So what happens in reality is, in systems, for example, in systems which kind of encode large-scale neural networks, they will use backpropagation, and we'll see that in subsequent slides. But they will not encode on whatever computation, and they will also use computational graphs. That's why we are studying it. But they will not explicitly write down these matrices, because, for example, as I said, think of 120. Let's think of a 100 cross 100 image. Okay, it has 10,000 pixels. So if let's say there's a there's a bunch of weights which are multiplying that input, which is 10,000 dimension, then one row of that weight matrix will also be 10,000 dimensional, right? Let's say that the one row of the parameter is a, so a is going to be 10,000 dimensional, and let's say h is output of h, let's say h is r dimensional, let's say it's 10. This matrix is going to be 10,000 cross 10 dimensional matrix. Okay, it's huge. So we are not really going to represent this matrix. That's why there are some clever things which the actual implementations do. But in terms of understanding, this is what is happening when you have multidimensional inputs and outputs. Okay. Any doubts for the scalar part and the vector part? This is the crux of backpropagation. There are many other resources that you'll find elsewhere which will talk about backpropagation by explicitly calculating the gradients and multiplying them through, let's say, a neural network or something like that. It's not needed. Backpropagation is all about computing using chain rule. In fact, just compute the local gradients, get something from your successors, and pass it back to your predecessors. That's the backpropagation of gradients. That's it. Okay. Okay. So given we have seen the example of backpropagation, each node has to just implement two functions. There's going to be a forward function and there's going to be a backward function. The forward function is kind of obvious, right? It's a computational graph. It will get input, let's say a comma b, from, it says from preceding nodes. Okay, it will get a bunch of inputs. It just has to compute, do its local computation, and just pass the output of its computation to the succeeding node, right? So that's what is the forward API, or some forward function in this object, in this node object. But it should probably also track the inputs and the local gradients. Local gradients, as I said, is kind of necessary if you want to get the final outputs gradient with respect to the input. So it will have to track inputs and local gradients. Okay, and the backward API or the backward function is gonna get a gradient from the succeeding node, compute the gradients, which is just a simple multiplication, maybe a matrix vector multiplication or scalar multiplication, and return the gradients to the preceding nodes of the computation graph. That's all. And the computation graph API itself is going to be, there's going to be a graph data structure, which is just a bunch of nodes. Somehow you represent the nodes and somehow you represent the edges. Okay, and the graph should also have two functions, forward and backward, where forward is just, you know, looking at the graph is just calling all the nodes which are on the left side, do your computation and keep moving to the next nodes, and finally graph is going to output the final scalar value, let's say, for instance the loss value. And the backward recursion is going to be just traverse from the right side of the graph back to the inputs, recursively traverse the graph backwards and return the gradients at the input side. That's all. I've just kind of written it down explicitly, but what's happening is what we saw in the 2 slides ago with every node. Okay. So given this propagation of gradients, okay, backwards, ultimately we find the gradient of the final output. For example, if it's a loss value, we find the gradient of the loss value with respect to the inputs in this way. Then we can map it back to our original problem. Let's recall what our original problem was. Our original problem was, for every parameter value, let's say w comma b pair in the linear classification example, for every w comma b pair I had a loss number L, right? I can pass all my training data, multiply it with w comma b in however way, and get the LIs. From the LIs I get the L data, add the regularizer, get the final number L. So for every w comma b pair there's an L, right? Now for a given w comma b pair I get the L number. Now I want to find the gradient of L with respect to these, with respect to every component of the w comma b pair. So let's ignore b for now. Let's say w is the matrix. Then I want the gradient of the loss with respect to every ij entry of the w matrix. That's all. That's all we want. Once we get the gradient of the loss value with respect to the parameter, we're gonna kind of update the parameter to the next parameter value. From w, let's say we are in iteration k, we can update it to k plus 1. If you remember gradient descent, it was wk plus 1 was wk minus some alpha times the gradient of the final loss with respect to w, right? So that's what we want to do, and we can do that efficiently using backpropagation. Okay, for any computation. So the mapping from the parameter to the loss can be any arbitrary lot, not any arbitrary, but let's say differentiable set of computations which are going from the parameter to the loss. Then we can backpropagate the gradients and make a gradient update, and that's what you can do. So the batch stochastic gradient descent, the batch gradient descent that we saw earlier is actually batch stochastic gradient descent, because we are not gonna do a gradient descent on L itself. We're gonna kind of take a subset of the training examples and just take a gradient on that. Okay, just take a loss on that and do a gradient update. So stochastic part, let's ignore it for now. We're gonna return back to why it's called stochastic gradient descent later. But we have seen batch gradient descent, right? So forget about the batch part. Gradient descent using backprop is just as simple as forward propagate through the computation graph, compute losses. Because there's a batch here, I'm just computing losses on the batch only and the regularizer, and get the loss, and backward propagate to compute the gradients with respect to the current w comma b, right? And then we update the w comma b in the direction of the negative gradient. And that's the gradient descent method with backpropagation thrown in there. Any questions? Any confusion with respect to notation, matrices, algorithm?
Do you change the batch for every iteration?
Yeah, so because the dataset size is large, like in the if you remember the ImageNet challenge, the data size is 1.4 million images, which you can't really do a gradient descent on the loss. Like 1.4 million images means the I index is going from 1 to 1.4 million, right? Now if you kind of pass all this data for a given w comma b, let's say you're sticking with linear classifiers, somehow your computed features, you're going to compute li for all the 1.4 million images, get the final loss number, and then propagate the gradient to get to update w comma b pair. That's too time consuming, so you will pick a batch, for example 100 images or 1000 images from the 1.4 million images, and only forward propagate for those 100 images, let's say, get the loss value and then propagate back the gradients, which means that you are not really taking the whole loss of the whole data set into account, whole training data into account. You're only looking at a batch's loss and then doing the update.
But is the batch constant when you do it?
No, you have to change it, and that's where the stochastic part comes from. You uniformly at random pick a batch. Let's say you linearly order, you have 1.4, let's say you have 10 numbers. You can do a choose, right? I can pick 2, 3, 4, I can pick 1, 2, 3, I can pick 4, 5, 5, 6, 7. Doesn't have to be like that way, but that's a way to pick a batch. Like n choose 3 or something like that. 10 choose 3, whatever. Okay. So that completes actually back propagation. Now we're going to look at feed forward neural networks, which are we'll just see what is the difference between a feed forward neural network and these existing multi-class logistic classifier that we just saw, which was the linear model, which was just wx plus b, transform it to scores, get the scores and classify, right? What's the difference between that and a feed forward neural network? We'll just see. Okay. So feed forward neural network. So the linear model that we had discussed till now was f of x comma the parameters, in this case w comma b, was wx plus b, right? It gave me, let's say it was 10 classes, f would output me 10 score numbers. I could have just taken the index with the highest score as my prediction for that test image, which is represented by x, right? A feed forward neural network is just similar to this, except it will include a bunch of non-linearities. Okay, so let's focus on what I'll call a two-layer model. Okay, so it will have instead of w1 b, it will have w1 b1 w2 b2. I'm explicitly writing down these parameters because they correspond to something called the weights on the network and biases on the network. So that's why I'm writing it explicitly. But you can just think of it as yet another function, right? This function has again input, which is one part is just going to be the image or whatever feature, a feature vector. And instead of having two parameters w and b, it has 4 parameters, w1 b1 and w2 b2. And the function is going to be very simple. The function is going to be get the input, multiply it with a matrix w, add some vector b, okay, take the max with respect to 0 and this intermediate vector, okay, and then multiply that vector, which is still which is going to be a vector, multiply that vector with w2 and then add b2. Okay, that's the function. I have explicitly written down the function. Of course, it has a max operation, which is somewhat of a non-intuitive function, but this is what a two-layer neural network would look like. I have note that I've kind of indirectly fixed what nonlinearity I'm using. It's called ReLU nonlinearity. We'll get to that in a few slides. But let's say if I had fixed this function with four parameters, this is precisely a feed-forward neural network with 2 layers. Okay. Why 2 layers? Because there's 2 pairs of parameters. That's all. W1 b1 and w2 b2. 2 pairs. Okay. So if x is d-dimensional, then I'm gonna have to choose a dimension for the internal for these matrices, right? I'll choose I can't see x is d-dimensional. My output or the number of classes is p. Okay, p classes. In between I can choose. I have a degree of freedom, which is what is the dimension of for example, the number of rows of w1 and number of columns of w2. Okay, and that's going to be some integer I'm going to choose as q. Okay, so the number of hidden nodes then will be q. We'll see the network later, but this is the intuition. So I have a degree of freedom. I can pick a number q. This is going to correspond to the number of hidden nodes. hidden because it's not interacting with the input and it's not interacting with the output. Okay, that's just jargon. The number of labels is p, just as we saw before, and the notion of layer is just for conceptual reasons and for vectorizing. So a neural network can be anything, right? I have a bunch of nodes, a lot of directed edges going from anywhere to anywhere. It's still a neural network, but we're going to look at certain types of neural networks which are layered, and this is what people do, and it's just for vectorizing or for conceptual reasons. Okay. So to be precise, the two-layer models function that I wrote here, right? Its diagrammatic representation is just this. The inputs are going from top to bottom. So okay, so the input layer is d-dimensional. Okay, the hidden layer is q-dimensional, and the output layer is going to be p-dimensional, corresponding to p classes. Okay. Of course, right here there's a question of how to pick the layers. Why two layers? Why just have one set of hidden nodes? Why not many other matrices, right? For example, here I could have taken a max operation of 0, this whole thing, and again multiplied with W3 and then added a bias B3 and so on, right? You can see that this is a recursive function. I can add another max operation outside, multiply it with W3, add another max operation outside, multiply with W4 and so on. So it can be possibly more layers. And in each layer, how to decide Q? Okay. The simple answer is you have typically people suggest that you use as many neurons as possible, as in as many hidden layers as possible and as many nodes in each hidden layer as possible, as in Q to be as large as possible, and hopefully if your computer can accommodate it or your computation power can accommodate it, then use as many layers as well. Okay. So the algorithm, which is the batched stochastic gradient descent using backdrop, is going to be the same as what we saw for the linear model. Okay, so we still choose a batch of sample size b. We forward propagate through the new computational graph. So the old computational graph would have looked like this, right? I get the scores, and then I use the logistic loss, the SVM loss or the multi-class logistic loss to compute one loss number with the regularizer as well added in. Instead of that computation graph, I'm going to replace some parts of the computational graph with this new function, right? Instead of the linear function here, I'm going to have a nonlinear function here. But the rest of it is the same. You compute losses on this batch, add the regularizer. Now the regularizer may want to include the additional parameters, right? The second layer's parameters, let's say. Get the loss number, and then back propagate for that from the final loss number all the way to the parameters, the current set of parameters, W1, B1, W2, B2, and then you do the regular gradient update of W1, B1, W2, B2. Gradient update is clear, right? It's just the current value minus some learning rate times the gradient with respect to gradient of the output, which is the loss with respect to W1 or B1 or W2 or B2. So that's the two-layer model. We just said, okay, why two layers and how many nodes in each layer? We kind of questioned that. We'll look at how to make these design choices again in subsequent lectures. But another design choice that we want to look at is what is called the nonlinearities. Okay. So there are three nonlinearities that we're going to focus on, but this is one of the recent papers from, I guess, 6-7 months ago, which is called Systematic Evaluation of CNN Advances on ImageNet. So ImageNet is the data set I was talking about at the very beginning of the class, right? 1.4 million images for the classification task, and in general, I think it had 15 million images, so a lot of images. So there, I think, so these guys have summarized all types of nonlinearities, which were used by various researchers, right, along with the year in which I guess the nonlinearity was proposed. So what do I mean by the nonlinearity? Just going back to this computation, from the linear model, when we went to the two-layer model, we introduced this nonlinearity, which is a max of 0, some vector. Okay, it's an element-wise operation, so you can just think of it as a scalar function for now. So it's just a max of 0, z. Okay, if z is positive, output z. If z is negative, output 0. So that's why it's a nonlinear thing. It's not outputting some alpha times z. If it was alpha times z, it was a linear function, but it's max of 0 comma z, then it's a nonlinear function. So this max of 0 comma the input is what is being done by this hidden layer. So the hidden layer will get wx plus b, okay, and will output either 0 or wx plus b, depending on whether wx plus b, that particular coordinate, is positive or not. Okay, if it is positive, it will output wx plus b. If it's not positive, it will output 0. So that's the nonlinearity sitting on the hidden layer. So let's focus on the nonlinearities, and then we'll actually kind of again look at these networks in the next lecture, because we'll get towards what are known as convolutional neural networks. So for today, we'll just focus on one block in the choice of a feed-forward neural network, which is going to be what nonlinearity should I use. The nonlinearity that we kind of described 2 slides ago is this nonlinearity, which you see y is equal to max of x plus 0. It's a nonlinearity, again I repeat, is because if x is positive, output x. If x is negative, don't output x, output 0. This is a nonlinear function. Okay. Yeah. So let's focus on sigmoid. Sigmoid is a function. Is a function which is again a nonlinear function. Let's think of the scalar function. Then it maps. So it gets input from whatever minus infinity to infinity, and it maps that and maps any number, real number, to an output which ranges from 0 to 1. So the sigmoid function is this 1 by 1 plus e to the power minus x. We have seen this multiple times in the previous few slides. So this is what a sigmoid function is, or I guess a logistic function is. The issue with this nonlinearity is what we're going to describe now. We're going to look at why this nonlinearity may make sense, why some other nonlinearity may not make sense. Okay, that's what we are trying to do here. So this was a nonlinearity that I showed in the previous slide as well. And in the computational graph, this is what a node would look like. If the node is doing 1 by 1 plus e to the power minus z, then that's a sigmoid computation node, right? Now let's say this is what a hidden node in a neural network also does, but let's just say that this is the node. This is a node here. Output is g, and that is being fed to another subsequent node, let's say, which is h. Okay, so h is passing its gradient. Now think back to back propagation. H is passing its gradient, grad h by grad g, right? Back to this node. This node is computing its local gradient, let's say grad h by grad z, because let's say z is the input, it's a scalar input, let's say. Then it just multiplies the gradient that it's getting with its local gradient and passes it back, right? That's what backprop was. Now let's try to see what happens when z is plus 100, let's say. What do you think happens? So z is plus 100. So what's happening at this node? So for z plus 100, what is the approximate value which is the output?
More than 100.
It's not going to be more than 1. It's close to 1, right? I mean, for input z is equal to 6 is almost 1. So it's going to be almost 1. So what is the gradient here? Like, right? It's 0. Yeah, close to 0. So grad g by grad z is going to be almost 0, and so whatever gradient was being passed from, let's say, a subsequent node, let's say this is actually the last computation node and is actually computing the loss, let's say, the gradient of the loss with respect to this node's input is going to be 0, because this node is what we call is saturated. So I'm just trying to point out some properties of, if I use this nonlinearity and the input was very high, then maybe when I'm doing backpropagation to update my parameters, w comma b pair, or in this case many other parameters, they may get saturated, and therefore gradients may not get passed down to the predecessors. That's all. Okay, and so the saturated node is making gradient vanish, and which is one of the probably a problem or a property of this particular nonlinearity. Another problem or another feature of this nonlinearity is the output is not zero centered. The output is centered at 0.5. Okay, output is a value which is from 0 to 1, right? So it's not zero centered. And so people have observed that when outputs are not zero centered, there's a there's an issue with the convergence rate of the first order method. So this is an empirical observation. Typically, if you remember from your data mining class, there is this PCA operation, right? So for PCA, you kind of remove the mean and kind of normalize your data before you apply PCA. Something like that. Here, let's say one hidden layer had the sigmoid hidden units, and all of them outputted some numbers. But the mean of these numbers is positive. They are not zero centered numbers. Okay, so when they go as input to the subsequent layers, it may cause issues with backpropagation or with respect to the convergence of the first order method. To at least get rid of the zero centering issue, there was another nonlinearity which was proposed, I think, around the same time, 1986, which is called the hyperbolic tan function, which looks like this. Okay, these dotted lines here, the dotted line here represents the tanh function. So it's just something like two sigmoids kind of reflecting, symmetric around the horizontal axis. So at least the output is now potentially going to be zero centered, right? Because the middle output is 0. But still it has the vanishing gradient problem, because when the input is very high, then by backprop no gradient will go through to the predecessors, and even when the input is very low, again the gradient is 0 and it will not go through. Okay, so to partially counteract that, another nonlinearity was introduced, which is what we saw in our few slides ago, which is called ReLU. Okay, the max of 0, z is just defined or whatever named as ReLU. It just stands for rectified linear unit. Okay, I don't know. So rectification just comes from, I guess, electrical engineering, where you have rectification of electric signals. Okay, but all it means is the following: if and the curve is shown on the right hand side here, the purple curve. So if input is greater than 0, then you just pass the input, and if the input is less than 0, you just pass 0, output 0. Okay, in the forward pass, that's what you do. In the backward pass, let's focus on backpropagation. Let's say we got back the gradient of some gradient, from our succeeding node. It's a max of 0, z, right? If z is positive, only then the gradient is, pretty much sent back. When z is positive, the gradient of this node is 1. Okay, and when z is negative, the gradient of this node is 0. That you can see by just looking at the curve, right? It's just gradient here, or the slope here is 1 and the slope here is 0, right? So this nonlinearity acts as like a gradient gate. When z is negative, it kind of kills the gradient, just like before, in fact worse than before, because previously at least there was a small number being multiplied with the incoming gradient. Here the gradient is essentially 0 when z is negative, and when z is positive, the gradient is nicely passed back. Okay. So empirically, this particular nonlinearity has been observed to be very, very good in terms of learning good classifiers. Okay, and good nonlinear classifiers. But the issue again is that because if z's happen to be less than 0, this node is kind of defunct. It could happen that because of how you start with a w, b or w1, b1, w2, b2 pairs, the initial candidates, it could happen that this node is never on the positive side, in the sense that the input is always negative. In that case, this node is never gonna do anything. It's always gonna output 0 and is never gonna send any gradient back to its input. So that is called that phenomena, or that issue is called the issue of dead ReLUs. Okay, that you can actually see by passing all your training data through your f, the f function, which was actually a hidden feed forward neural network, and just seeing if some of these computation nodes never kind of gave any value other than 0, right? You can kind of statistically just see whether, let's say I passed 100,000 examples, but this node never outputted any value other than 0, means that this ReLU is dead. In the sense, the input is never going greater than 0, and that's probably because the weight times the input images pixels or whatever input feature vector is never crossing a value greater than 0. So that's the kind of some description of the 3 nonlinearities. Okay. Now let's kind of finish this with one thing, which is neural nets. Why call this neural, right? I guess you might have already seen why these nonlinear models in this particular which are represented as these directed graphs, why are they called neural? Because of historical reason. If you think of this linear model, in fact this linear model where W is just a vector, okay, so this is a dot product, then this linear model was kind of proposed back in 1957 and was called a perceptron, okay. And given this linear model, the scoring, the classifier was very simple. If the linear model was outputting a number less than 0, then it would be one class. If it was outputting a number greater than 0, it was another class. And they, at that, so many years ago, 60 years ago, they had an update rule which is similar to gradient update, okay, where the current candidate of the parameter was being changed with respect to what happened on the current data. In the sense, let's say the current data point x is true, label is y. What did my classifier predict? Whether they are different, because it's just 0 1s, right? Y can be 0 and h can be 1, which means I mispredicted. Then I'll do an update of my parameter. That's all is happening. But they did not have all this notion of very proper gradient update and no notion of backpropagation. Okay, it was just a ad hoc heuristic which was proposed. Of course, there are guarantees on why this heuristic would work, but that was the starting point. After that, some other models were proposed where the score function was now being passed, was being transformed like this, which is precisely a logistic function, right? And then this transformation was kind of likened to how a neuron fires. So just think of it this way. Let's say f is still a linear model like this. F is w times x plus b. Okay. Then you can think of a neuron which has, let's say w is 2-dimensional, x is 2-dimensional. Then you can think of a neuron as having 2 inputs from other neurons. Okay. Those 2 inputs are getting multiplied by weights, w1 and w2. Those 2 neurons are those 2 numbers, w1 times x1 and w2 times x2, are coming in as inputs to this neuron, and given that sum of w1 x1 plus w2 x2, this current neuron is going to fire, as in is going to output a 1, maybe with this probability. Okay, this is a number which is again between 0, 1, so you can think of it as a probability of firing, or basically a firing rate. And so some analogy was derived, and therefore the neural name stuck. That's one version of why the neural name stuck. You can probably find other explanations. Okay, so let's kind of look at the software aspect of this course, as one final thing in this lecture. So we are going to be trying to use something called TensorFlow and something called Keras. How many of you have Windows machines? Okay. How many of you have used VirtualBox or VMware before? Okay, so we will need so potentially for your experiments. So we are not going to look at really large data and really large neural networks, but whatever neural networks or any other work that we're going to do in assignments or project, it will be probably useful that you kind of use Python. Python is fine. You can install it on Windows as well. But you may also need TensorFlow. Okay, and it I think has an issue with installation on Windows directly. So you may need a virtualization. So something like a Linux, like Ubuntu or something, on your VirtualBox would help for Windows users. Okay. So what is TensorFlow? TensorFlow is just the codification of whatever we discussed, some parts of it. So it's a programming system which represents computations as graphs. So whatever we saw, in the backpropagation chunk of the lecture slides today, that's what TensorFlow does. Basically, it has two steps. One is to construct this computation graph, whether it's a neural network graph or multi-class logistic regression graph, or even some other function. It can construct that graph, and then it has the right data structures and algorithms which kind of take care of the gradients. So the gradient propagation, and the software, the system itself takes care of, and you execute the graph, as in run the forward propagation and potentially the back propagation and so on once you execute the graph. And in TensorFlow language, execution just means the graph is kind of pinned down to physical resources like CPUs and GPUs. That's all. So TensorFlow is kind of very useful, and I think quite popular for kind of trying out deep learning network architectures. So let's try to use that. Actually, in the last few minutes, last 10 minutes, let's look at this one, I think. So, okay, I think you can't even see what's happening, right? Okay. So, actually, probably we need to. I don't want to touch the lights. Okay, I don't want to touch the lights. So let's. So basically, playground.tensorflow.org is what I mentioned here. So here you can actually kind of. I think the default page directly loads a 2 hidden layer neural network. So let's reduce the. So let's get rid of. Let's get rid of hidden layers. Okay. Then actually what it does is actually what we saw in the slides. So what we saw in today's lecture is just going to implement the multi-class logistic classifier. So the f is equal to wx plus b, and the loss is going to be the cross entropy loss or the logistic loss. So 0 hidden layers is what that the first model that we looked at. Okay, here they're showing two inputs, x1 and x2, and their data looks like this which is shown on the right hand side. It has two classes, the blue class in the center and the orange class outside. So and it has a few other parameters, regularization you can add, L1 or L2. The other parameters don't make sense when you don't have hidden layers, like activation and so on. Problem is classification, and if you try to let's say run your gradient descent in the browser, then it's not really doing anything. Training loss and rest loss is 0.5. Okay, but if you let's say add one hidden layer, okay, let's say it defaulted to 2 neurons. Let's pick 3 neurons, and we'll see what happens with 2 neurons. And let's say activation we pick ReLU, and some learning rate, regularization rate. Okay, I set it to 0. Okay, some regularization. You can tweak with these parameters, and let's say we click this button. All it's doing is gradient descent. Okay, so these are the you can see that the test loss is 0.02 and training loss is 0.01. So it has actually kind of figured out the decision boundary within which it can classify the blue examples and the orange examples. Okay, what happens if you increase neurons? I can't increase that, I guess. Yeah, if I increase neurons and then let's say run, you can see very similar test and training errors. Okay, So it's a good web page to try out whatever you learned today. Okay, because we have learned how to have one hidden layer with some number of neurons, and we also saw the logistic classifier, linear classifier. So that's that. Yeah. Okay. Okay, so I think that's all for today's class. There's some appendix slides, but we'll not get into that. So any questions today? To summarize, we looked at a few things. We first started by just looking at the whole classification process from scratch. We looked at what is data, what are models, what is the loss function, and how to optimize. Right? We kind of just got an idea of, okay, we need to optimize, we need to specify a loss function, we need to specify a model class or a family of models, and we know that data has peculiarities. That's what we did in the first part. Second part, we looked at backpropagation as an important tool to perform optimization, and it was a systems perspective where any objective that you want to optimize, if it has a bunch of constituent computations, then you can cast it as a computation graph, and then let's say given a w comma b pair, you can forward pass and get a loss number, for backward pass to get the gradients, update the w comma b pair to w prime b prime, again forward pass to get a loss number, backward pass to get the gradients, and so on. That's what we saw with backpropagation. Then we saw feed-forward neural networks, which are very simple neural networks, which we didn't see elaborate neural networks. We just saw pretty much multi-layer perceptrons. But we saw that, okay, we need to probably choose. There are some choices to be made in terms of the number of layers, maybe even if the layers is fixed, how many neurons per layer, and also the non-linearity. So those were the topics that we covered today. So hopefully in the next couple of lectures, we'll try to get a little bit deeper into the state-of-the-art neural networks, which is a family of convolution neural networks. Okay. So any questions you can ask me after this class, which is now. Okay. Thank you.